All right, I'm going to be doing the solution to the second problem of the quiz. So I have the problem statement up here. Consider a piston cylinder that has nitrogen gas, and then it gives some information about the states. So we're going to start off by writing out the state information. So it says initially the system is at 1 megapascal, and the temperature is 427 degrees C. This piston cylinder undergoes some process that keeps a constant pressure. Isobaric means constant pressure. And the temperature changes to 27 degrees C through that process. It asks to find P2 and Q, and this is going to be little q, which is in kilojoules per kilogram for this process. So since it's isobaric, the first given is very easy. We already found it, so because it's isobaric, we know the pressure doesn't change. For finding Q, we will need to think a little bit more about this problem. So we're going to start by writing out our physical laws. So anytime we're asked to calculate Q, we want to think of using the energy equation. So the energy equation for a closed system is that the change in total energy between the two states is equal to the heat minus the work. For this problem, there is going to be boundary work because it's a piston cylinder, and you also can start thinking of some assumptions to simplify. So the first one is that there was no mention of kinetic or potential energy, so those are both going to go to 0. And then you could also write the only work is boundary work. So if we know that the work is boundary work, we can write out the boundary work equation. And because it's isobaric, we can even write that the equation is constant pressure boundary work, where it's just the pressure times the change in volume. So if we put some of those physical laws together, we're going to have delta kinetic energy, delta potential energy, plus delta internal energy minus W, Q minus W for the whole equation. We said these are 0, and we said this is boundary work. So let's go ahead and plug those in. And this is where there's actually quite a few ways to do this problem. If you want to use the tables, then you can combine internal energy and P delta V to get enthalpy, and that's a pretty good way to do it. You can also calculate this boundary work and use specific volume to look up internal energy, or you could just use the tables for all the values as well. So I'm going to do the way that is the easiest way, which is I'm going to first solve for Q. So this is the equation. Now there's just a lot of different ways you can approximate these things. So the first way is delta U plus P delta V is the same as delta H. And delta H is the same as M times little delta H. And then we're looking for little q, which is the same as saying big Q over m. So big Q equals little q over m. So we can cancel those out, and we can write that little q equals delta H. Now, looking back at this substance, the substance is nitrogen. So we can assume an ideal gas for nitrogen. And when a substance is an ideal gas, the approximation for internal energy, or enthalpy, can be simplified a lot by just using specific heats. So since we have already converted this to enthalpy, we'll go ahead and use that. So delta H just equals Cp0 times delta T. And that's only true if you have an ideal gas. Otherwise, you would need to use table values for those H's. So what we're going to do, since we do have temperature values, is we're going to go ahead and use that relationship. That's Cp0 times delta H is the same as changing delta H. All right. So we have Cp0 equals times T2 minus T1. So we have T2 and T1, so we just need to look up the Cp value for nitrogen. So this is in table 5. So I'm going to open up tables here. We're going to go to nitrogen, go over to the Cp value for nitrogen, which is 1.042. So I'm going to jot that down here. Cp0 equals 1.042. And the units on that are kilojoules per kilogram Kelvin. And so going down and plugging that in down here, I'm going to get that 1.042 kilojoules per kilogram Kelvin. And then since this is a change in temperature, if you remember that changes in absolute and relative temperatures are the same, you actually don't have to even bother going through and plugging in calculating the Kelvin. You can just keep it in. You can just keep it in Celsius. So I'm just going to go ahead and plug in the Celsius differences. And then when I write in my units, I'm just going to write them in as Kelvin because that difference is the same in either. So we have 27 minus 427 there. So you're going to get about minus 400 here times 1.042. And if you do that, you'll get a final answer of negative 416.72 kilojoules per kilogram, with the Kelvins canceling out. And that is your little q. So other solution methods. You could use table values. For delta H, and so you could just start with this start equation, and you could just look up table values for H and use that. You could start with equation star star, and use that delta U equals CV not delta T, and then use the ideal gas relationship for the other values. Or you could do some combination of table values and ideal gas, and specific heats. You can really combine them. The method that I showed you here is just the one that takes the least amount of work because it just involves specific heat approximation of enthalpy. So anytime you can do that, you do want to because it's easier. So for this middle step here, what I mean by ideal gas is that you can say that PV equals MRT, and you can replace PV here with RT and then use the T values that you were given. So they all give you about the same answer. All right, so all those are good solutions. This one is just the easiest. All right, hope that was helpful. Thanks.